Hello and welcome to today's session on noise and vibration and electric machines. My name is Dodo Husman. I am your host for today, and I have invited Mitch Marks, our business developer for electric power testing, to introduce us to the topic of noise and vibration. This is the second part of a three-part Lunch and Learn series on electric power testing. I will now hand over the word to Mitch and wish you all a lot of fun.
All right, thank you, Dodo, and thank you everybody from what appears to be around the world joining. I know it's a weird hour for some of you. As Dodo mentioned, this is the second installment in a three-part series. This specific presentation will have a follow-up presentation in a couple of weeks. So if you like what you heard here, this is an introduction, and the next set will be going into more detail of data taken, analysis done, conclusions received, but we need to start somewhere, so we'll start with an introduction to noise and vibration in electric machines. If I can figure out how to work my PC. Oh, all right, here we go. Quick agenda. So this will be an introduction to vibration in electric machines. Just kind of go over what the sources are, where we need to look for it. Characterizing noise, vibration, and harshness in electric machines, what some of the characterizing features we look for are. So this is like why we care. The reason behind testing both, I think historically, a lot of companies have a noise and vibration group and also a electrification group, or maybe the electrification group's new. But there's a trend to bring these two groups together. And I think the main reason that I'm presenting this is to really enforce in all of us here why this is important to measure these two things together. Why do we care? Why do electric guys need to learn noise and vibration? Why do noise and vibration guys need to learn electrics? And then we are a company who sells something, so while this is meant to be academic, we'll go over our eDrive solution. So here it is, introduction to noise and vibration, or introduction to vibration in electric machines. So first of all, we'll start with a little bit of an overview of the electric powertrain, because at the end of the day, this is all a physics problem. And we have a battery, I'll get my pen, with DC electric current that's going into an inverter. This inverter is turning on and off switches at tens of thousands of times per second. So a pulse width modulated signal, where we're turning this DC energy into this PWM, and I apologize for my bad handwriting, AC. So we're going from DC to AC, and we have this high frequency content. This high frequency voltage and current is then going into a motor, and we're creating high frequency magnetics. And then these high frequency magnetics are creating high frequency torque. And a lot of this gets averaged out to be a nice DC. But if we really analyze it in the detail, we're going to get noise that's created by this high frequency magnetics and noise that's originated with this high frequency voltage. So it's really DC voltage to AC voltage to magnetics to torque and speed. Now this torque and speed also has a rotational element, and this rotational element is going to also have things like torque ripple that we discussed yesterday, or order effects, resonances that are going to have their own excited noise and vibration, or go into an output like a propeller or a transmission, which have their own series of effects. And why we care about all of this is, one, our experience as a driver. We don't want to hear this really terrible high-pitched whine at a certain speed. And also from a durability and fatigue issue, vibrations or noises are indicators that things are going wrong, and we don't want parts failing early. So that's just a little background on this is all one big physics problem, and what's happening in this piece of circuitry in the inverter is going to end up in the mechanical output. And if there's noise here, it might be caused over here. And we really want to do that root cause analysis and know why things are happening. So what are the sources of noise and vibration? Again, people from yesterday, this might be a little review, but it's all good stuff. Motor construction is a source of vibration. And if we think of it, this is a piece of a motor, stator and rotor. And in the gray, we have the stator, and in the green and the brown, we have the rotor. And these little colored dashes here are the windings, and these windings have three-phase AC current going through them. This is what we just discussed in the previous section. Well, our intention is to get rotational forces, so we want this torque being produced in the rotational direction. But as we excite that current to go radially, there's an equal and opposite force that's going out into the stator. And if we're turning on and off this inverter, turning on and off this switch at tens of kilohertz, we have this excitation force going out at tens of kilohertz. And if this structure, the stator, has a natural frequency or has resonances, we're going to excite that structure, and we're basically exciting a big speaker. So that's one source of both noise and vibration. Another one is that this machine has a physical construction, and these magnets, highlighted in the brown, want to stick to this gray iron. And each one of these magnetic tips wants to stick to that chunk of iron. And if we ever have grabbed the shaft of a motor and you try to spin it, you get this ba-dum, ba-dum, ba-dum. It's these magnets trying to stick to these teeth. And at a static position or during rotation, these magnets want to stick to these teeth. This creates a thing we call torque ripple. It's a function of the number of magnets and the number of slots. And what this is really doing is it's creating some vibratory effects from the speed of rotation that are going into the shaft. So again, hitting on the previous point, we have two sources of noise and vibration: rotational speed, and then also that inverter switching that's creating that magnetics. So it's really interesting. We have this kind of low order noise and vibration from rotation, and then this higher order from the switching effects. More on switching effects, because this inverter is a function of excitation. What I have on the right-hand side are two examples of inverter switching. So on the top, I have a PWM signal, a pulse width modulated inverter command, where we're turning on and off that switch at these kind of variable pulse widths. And if we filter this out, we end up getting a nice smooth sine wave. But each one of these pulses is a voltage, goes to a current, goes to torque. And because we're doing this, these are individual pulses that are going to create a noise and vibration effect at that high frequency, at that switching frequency. So that's an example of a PWM. PWM makes a really nice sine wave. There are other control techniques, like a 6-step, which I have featured down here in the bottom graph. And what I have shown are voltage in blue, where we have this kind of 6 discrete steps in voltage. These 6 steps in voltage get translated to our current. We see that our current has the shape of a sine wave, but it's really got these jagged peaks. And these jagged peaks are harmonics. And if we translate from these jagged peaks and harmonics, and we look at our torque signature in pink, we can actually see that when we turn this switch on, we get a spike in torque. And when we turn this switch off, we get a dip in torque. And this torque is directly correlated to that voltage and to that current. And again, this torque is exciting, a shaft. It's exciting what's downstream in something like a gearbox. And there are a lot of control techniques. And anytime we're pulsing current or we're pulsing voltage, we're pulsing torque, and we're creating forces outward. Now, if we take this a step further, we're talking about noise and vibration here. If we look at something like this inverter effects on a frequency, we can find that torque has a frequency component. So if we look at again, this is the exact same example from before. If we look at this voltage, on the left-hand side, we have a really smooth PWM pulse width modulated type voltage. This results in a really sinusoidal current, which results in a torque that has some ripple due to excitation effects, but it's relatively stable. Now, when we switch that control technique and we operate the inverter in a different method, this is what we call a 6-step. and we have significantly fewer switches per second. So on the left-hand side, we have 13 kilohertz, and on the right side, we have 500 hertz. And we can see that we get that high harmonic content in the current, and then in that torque, we get these really wild torque swings. And again, these are going to result in noise and vibration downstream. This inverter controlled voltage and current is going to create torque ripple later in the path. So now the noise and vibration people, they like to look at this in the frequency domain, and that's exactly what we're going to do here. So I have my current on the left and my torque on the right, and I have that left-hand side of the graph, that PWM is highlighted in blue, and my 6-step is highlighted in red. And we can see in the current FFT, and this is just an FFT plot that I have here, we see a big peak at the fundamental in both. We expect that. But if we look at the fifth harmonic, there's almost no fifth harmonic for the PWM, but we have a huge fifth harmonic for the 6-step. This is telling us that we have additional losses, we have additional torque ripple, we have additional issues. We also see the 7th harmonic and some subsequence in the current. Now, if we go over to the torque, we see a big spike at 200 hertz. I believe this is a function of the number of poles because it's a 4-pole machine. We see a spike around the fundamental. But we also see a very large spike at the 5th harmonic. And if we note it over here, we have a 5th harmonic caused by the 6-step. We have a 5th harmonic caused by the torque. And then we have another harmonic over here at 600 hertz. This is a function of the switching. So we can actually see that switching content in our torque. And what this is this is that frequency content. This is that thing that's going to result in noise and vibration. If we go to a vibration spectrum, we're probably going to see spikes at 600 hertz and at, what is this, 250 hertz that are resultant of that electrical current. So it's all one story, it's all one path. Now, along that same note, if we were to take current and vibration, we can see that from our rotational effects in blue or black, we have frequencies in both vibration and current that correlate very closely to one another. You know, the peaks are at the same frequency, they're just at different amplitudes, which is really a transfer function. So we have this root cause of current to vibration. If we look at our inverter switching in green, again, we see peaks at the same frequencies. So again, we have this root cause that maybe this is noise being transferred out to the housing, or noise being transferred to the driver of the vehicle. Lastly, this specific inverter had another field switching where, again, we have this 20 kilohertz carrier frequency that's being translated into the vibratory function. So we can really closely correlate current and vibration, or current and noise. Torque sensors often have a bandwidth limit of up to 6 kilohertz. So you can also use a accelerometer or vibration measurement as an indicator of your torque ripple out beyond a given frequency. So all the presentation I gave yesterday about torque ripple is really showing up here again, because current goes to torque, goes to vibration. So it's a really, really cool phenomena, and they're all linked together. This is a quick one. What we really commonly see and almost always see is that as you increase current loading, so as you put more current, more torque into a machine, the level of vibration increases. And this was just a test that we ran at 3 different load states. So we ran at 0 torque, 13 newton meters, and 26 newton meters. And if we look at the vibration spectrum, as our torque increases, the amount of vibration increases as well. This isn't surprising, but these are directly correlated phenomena. And if we're really worried about things like gear mesh, we're going to see a drastic increase in gear mesh orders as we increase loading. And there might be certain circumstances or resonant modes or given operation points where torque ripple's higher and potentially gear mesh orders are higher. So looking at these things, and again, thinking downstream, what's happening in the gearbox, what's happening in the transmission, can really be indicated by current and seen in vibration. A common plot used for understanding rotational machinery is a spectral plot, where you take a machine, you fix a loading point, and you sweep from 0 to a certain speed. And this is a plot of frequency content on the X versus rotational speed on the Y. And we can look at both current and vibration in one of these plots, and we can see that these lines, these darker lines, um, at the angle, are indicating harmonics or orders. And what we can see is that my fundamental is this really bright yellow one on the right. That's my fundamental and my current. And then we have subsequent orders or harmonics coming off of that. And I have highlighted in the red here the fifth harmonic. This is from that previous example I showed. If we go to our vibration, we can also follow that fifth harmonic in the vibration spectrum. So we can really start to use the same tools that we would use in noise and vibration for analyzing current. So if you're doing a noise and vibration test and you really want to understand the root cause of your vibration, you can bring in a current and really have that cohesive understanding and look at it with the same tools you have previously. And this graph was actually made in BK Connect, which is a product of ours. So why measure both? Kind of the crux of, we've gone over what is torque ripple, where does it come from, why we care. Since there's so much carryover between current and vibration, or current and torque and vibration, we can really start looking at doing a single test to do both measurements and really reduce capital costs, especially for startups or new groups. If you make a change in an electric machine to increase efficiency, you might hurt noise and vibration, which comes into vehicle experience. If you make a change in noise and vibration to increase the experience, you might hurt the efficiency, which right now is a paramount. So we really need to increase communication between groups, because we want to optimize this system. We want to have a very enjoyable vehicle experience mixed with a vehicle that can go as far as we need it to. So if we can increase communication, we can speed up development and get to market more quickly. Also, in this era of trying to push to more simulation, we're really going to increase the communication of vehicle simulation, because we can give them the voltage state, the current state, the torque state, and the vibratory state, and really give them a full data set to understand the vehicle. So communication, I think, is probably the biggest one. Is let's reduce time that it takes communicating with our sister groups. We're seeing an increase in people trying to design sound into the machines. And anytime you're going to introduce noise, or an enjoyable noise, there's a chance you reduce efficiency. So that again comes back to communication. Let's speed up development, get an optimized product. Fatigue characterization. If a vibration or a resonance is causing fatigue, gear failures, again, it could be caused by magnetics, and increasing those communication lines will help us get to root causes sooner. Then resonance tracking, end-of-line characterization. And what I have in the graph on the right is just a ramp of voltage and current as we speed up a test. So we see voltage and current go up. This was actually a lift fan for an electric aircraft. We see loading go up. So this isn't just an automotive problem, this is also an aerospace problem. And then we see the vibration go up with loading. That loading decreases, we see vibration go down. So these things are all correlated. They're all root cause, and we can start to identify problems more quickly, communicate more quickly. Again, we are a company, we sell something. And what we sell, we call the eDrive solution. All the tests I showed earlier in this graph were done with eDrive test equipment. And what the eDrive system does is it's a power analyzer. It gives very accurate power and efficiency measurements, but we can also bring in electromechanical signals, so we can measure accelerometers, we can measure many torques and speeds, many voltages and currents, a wide variety of sensors, all with one system. We like to think we can future-proof, if you look at this chassis here, it's got 7 slots. So these guys are our card slots. From these 7 slots, you can add up to 7 cards, which buy you voltage and current, or torque and speed, or vibration. So you can really customize your test, and you could start with 2 cards. And if in the future you want to add a dozen accelerometers, you can add an accelerometer card. So you can really future-proof your testing capabilities. If you don't have noise and vibration needs today, and you do in the future, you can always add them in. Our tests are auditable. We record all the data that goes into our power and efficiency and vibration measurements so that you can really go back through the data and understand what happened in a test and why. Everything is time aligned so that you can really correlate things very closely, especially if you start getting into weird control techniques where you're pulsing currents, you're pulsing torques, and you might be causing asynchronous vibrations. You can understand that. Full data streaming, know where your results came from. This is right along the same lines. Everything we measure, we're measuring the raw data of, we're doing calculations, and we can actually feed those back to an automation system. So you can really put our system in a hardware in the loop system and store all that data so you understand where it came from. And many of you probably know us from our HBM torque sensors. We like to think, and we effectively do, simplify the measurement chain. We make sensors, we pair them with our acquisitions so we can measure the full bandwidth of a torque sensor, so we can measure the full bandwidth of an accelerometer. And then we also have analysis software. And I evidently didn't save my changes because I did have a picture of our BK Connect noise and vibration software, but we can do analysis of electric machines, efficiency mapping, and then things like the spectrum graphs, rain flow charts, a lot of the noise and vibration measurements as well. So I hope you guys enjoyed my presentation. I hope you learned something. If you'd like to ask questions or learn more, please reach out to me on my LinkedIn. Or if you want to learn more about our products, you can scan these QR codes with your phone to reach that. And again, this is the introduction part of a 2-part series. So we will announce in a couple of weeks the next part of this, and I hope you will join us for that as well. So Dodo, back to you. I don't know if we have any questions that I've covered.
Thank you, Mitch, for this really great presentation. We do actually have a question. Before that, I want to remind all of our participants that we have recorded yesterday's session on torque ripple and today's session on noise and vibration, and we will make the presentation and the recording available to all of you by the end of the week. We also hope that you're going to join us tomorrow on an introduction to measuring electric power during transients. Mitch, I'm just going to read out loud one question. Can I bring in vibration along with using the eDrive system on my Gen 7 TA?
Yeah, and let me, if I can get back to my presentation. In your Gen 7 TA, glad you're a customer. Thank you. Appreciate it. You likely have these 2 voltage cards. You would add an additional card, which is what we call, well, we have a couple of vibration cards, but I think most people probably use our GN840B. That's a product name, but what it is a universal card. So it offers IEPE excitation. And then you would just connect your accelerometer via the BNC connection to the card. You'd have that IEPE excitation, and it would just bring it in and read it in engineering units. It's pretty quick and easy.
Thanks, Mitch, for answering the question. Thank you, everybody, for listening in, for grabbing your coffee and joining us for our Lunch and Learn series. Hope to see you tomorrow and wishing you all a nice day.
Thanks, everybody.
Thank you. Bye.